So let's continue thinking about compounds and their chemical formula. Take special note of the subscripts on a chemical formula. Those subscripts tell us certain things about that certain molecule. So those subscripts tell us the ratio of atoms that are present in one of those molecules in that formula. But what those ratios will also tell us is the molar ratio of each element when you have a mole of that compound. So what I mean by that, let's look at this example. Glucose has a chemical formula of C6H12O6. So if we think about one molecule of glucose, there are 6 atoms of carbon, that's denoted by the subscript here. There are 12 atoms of hydrogen, and there's 6 atoms of oxygen. Taking note of those subscripts. That's when we're talking about one molecule. They're composed of atoms. But if we had a mole's worth of glucose, then 6.022 times 10 to the 23 molecules of glucose, that's 1 mole. So if we have 1 mole of that glucose molecule, then we would also have 6 moles of carbon in that sample. We would also have 12 moles of hydrogen in that sample, and we would have 6 moles of oxygen in that sample. So see, when we're talking about molecules, we are talking about atoms, single individual atoms of the different elements. But when we're talking about a mole's worth of a certain compound, in this case glucose, we're talking about moles worth of each of the different elements denoted by the subscript. This is really important differentiating whether we're talking about a single molecule or a mole's worth of a molecule. So I'll show another example here because this is kind of the cusp between the microscopic and macroscopic realms, where macroscopic is lab values that measurements we can make in lab. So here is caffeine again, the chemical formula for caffeine. So we can take those subscripts and still apply the ratios that I was talking about before. If we had one molecule of caffeine, we're talking about atoms. There's 8 atoms, there's 10 hydrogens, there's 4 nitrogen atoms, and there's 2 oxygen atoms. And we could take the weights of those atoms off of the periodic table and get that unit in AMU. The weight of one molecule would be an AMU. But if we want a larger scale that we could actually measure in lab, we want to be talking about moles worth of caffeine, this particular molecule. So a mole's worth of caffeine will have 8 moles of carbon in the sample. There will be 10 moles of hydrogen in the sample, 4 moles of nitrogen, and 2 moles of oxygen. This puts us in a unit that we can actually measure in lab, and that if we added all of these numbers up to get a molar mass of caffeine, our unit would be in grams per mole. And you would calculate either the molecular weight of one molecule, and that would be an AMU, versus a mole's worth of caffeine, that would be calculating the molar mass, and that would be in the unit of grams per mole. But you calculate it the same way, just taking note of the ratio of atoms or the different elements in the formula and using the periodic table and those weights off of the periodic table to get either the molecular weight or molar mass. You calculate it the same. The only difference is the unit that is involved in that final value. So let me show you some examples of types of problems that I could ask relating to the subscripts of chemical formula. So here I have a question. We're going to use that chemical formula as the ratio that I kind of showed up here. That 1 mole of caffeine equals 8 moles of carbon, or it equals 10 moles of hydrogen, etc. So those are new qualities that we can use in our dimensional analysis unit conversion problems. So this question, it says, how many moles of carbon are in 0.75 moles of caffeine? So, and it gives us the molar mass here. But see how we're already in the unit of moles of caffeine? So if we take a look up here, back up here, where we said 1 mole of caffeine has 8 moles of carbon atoms, I can write a new equality. 1 mole of caffeine equals 8 moles of carbon atom. Or it equals what, 10 moles of hydrogen atoms, or it equals 4 moles of nitrogen, or 1 mole of caffeine equals 2 moles of oxygen. So these are new equalities that we can use to convert between moles of a molecule and moles of a certain atom that it's asking for. So in this case, it's asking for moles of carbon. So we're going to use this first equality, moles of carbon, 1 mole of caffeine equals 8 moles of carbon. So I'll show you how that works out. So if I'm going to start with a number that they give us, we have 0.75 moles of caffeine. And I'm going to use that first equality. 1 mole of caffeine equals 8 moles of carbon. If I have a mole of caffeine, there are 8 moles of carbon there. So I'm going to essentially multiply the moles of caffeine by 8 to give us moles of carbon. But I'll show you that the units cancel out too. 1 mole of caffeine over 8 moles of carbon. So see how moles of caffeine cancel, and now we're just left with moles of carbon. So if you stick that, into your calculator, you will get 6.0 moles of carbon. So you can go, we could figure out moles of hydrogen also. We wanted to do that. In the same sample, if we started with moles of caffeine, there are 10 moles of hydrogen for every 1 mole of caffeine. And remember, these numbers just come from the chemical formula itself. And so you see that there are 7.5 moles of hydrogen. So maybe on your own, you can determine how many moles of nitrogen are in the sample and how many moles of oxygen are in the sample as well, using the ratios that I laid out up here. So that previous example was just a straightforward moles of a molecule to moles of a certain atom in the chemical formula type of conversion, where we use the ratios in the chemical formula itself to get to moles of a certain atom. So in this example, this is an example that's more likely to be presented on an examination because it's a little bit more involved. Instead of just giving moles of a sample, I give you grams of a sample. So let's walk through this question. It's a little bit more involved. So Prozac, it has this chemical formula, is an antidepressant that inhibits uptake of serotonin by the brain. So the first question here, what is the molar mass of Prozac? So note what it's asking for, molar mass. We know that that has a unit of grams per mole. So they give us the chemical formula, so we can go ahead and just take inventory of all the different atoms that we have there. So there are 17 carbons. Carbon has a molar mass of 12.01 grams per mole. There are 18 hydrogens, 0.008 grams per mole. There are 3 fluorines. Fluorine has a molar mass of, what is it? Oh, do I have it here? Yeah, it's 19.00 grams per mole. There's 1 nitrogen that has a molar mass of 14.00 grams per mole, and then an oxygen that's 16.00 grams per mole. So if you take into account the subscripts and the 17 carbons and all that, put that into your calculator, you'll get that the molar mass is 309.324 grams per mole. This is an addition problem. And so since we're adding here, we're going to round to the hundredths place. So our answer here will be 309.32 grams per mole, because this is addition. So that's the molar mass of Prozac. I got that from just taking inventory of all of the different atoms in the chemical formula and using the periodic table. All right. So how many molecules of Prozac are in a 15.9 gram sample? So remember, our conversion chart, if we want to go from grams to moles to molecules, we have to go through it in this order, molecules, right? Where we use molar mass to get between grams and moles, and we use Avogadro's number to get between moles and molecules. So I'm going to just go on a different page here. So I have 15.9 grams of the compound Prozac, and we want to get to molecules. So we're going to start in grams, and we want to get to molecules. So we have to use moles to get there. So if I start with 15.9 grams of Prozac, maybe I'll just write those conversions in the corner here. So the conversions that I'll be using to get to molecules, well, the first one will be Avogadro's number. 1 mole of Prozac is equal to 6.022 times 10 to the 23 molecules. And I'll also be using the molar mass to get between grams and moles. And we got that, it's 309.32 grams of Prozac equals 1 mole Prozac. So let's see. So right now I'm starting with the number that the question gave us, and that's 15.9 grams. So you see here all of the equalities that I have. There's only one that has the unit of grams, so I'm going to put that on the bottom. 309.32 grams. That's equal to 1 mole of Prozac. So now I'm in moles. I'm here on our little chart. I went from grams to moles. So I could stop here and get moles of Prozac if that's what the question was asking, but it's not asking that. It wants molecules. So I need to go one step further and get to molecules, and I'll use the conversion factor that I haven't used yet, where 1 mole of Prozac equals 6.022 times 10 to the 23 molecules of Prozac, right? And so I'll show you how all those units cancel, grams cancel, moles cancel, and I'm just left with molecules. So I'll show you now how to do that on the other calculator that I have here. Okay, go, move the camera. Okay, oh, I should probably make this bigger. All right, so I have this kind of calculator. In the midterm, I saw many of you had this kind of calculator. All right, so I'm going to just go ahead and put those values in. So 15.9, all right, divided by 309.32, all right, and then times 6.022 times 10 to the 23. So this is, again, one of the scientific notation numbers. So on this calculator, remember how in the other calculator I told you there was an EE button? There is also an EE button on this calculator. It's right here. It's right here above the x to the -1. You need to press the second button in order to get to that. So I'm going to write 6.022 second, and then EE. So there's a little E that shows up, and then you put the exponent, 23. So see how I wrote 6.022 E 23, where E replaces the times 10 to the. All right, and so there's our answer. So our answer is 3.0955 times 10 to the 22. So I'll just show how to do that exponent stuff again. So again, if I wanted to put in Avogadro's number into the calculator, I would write 6.022 second EE, which is right here. It's above the 7. So there's an E, 23. All right, if I press equals, you see here that the calculator spits out Avogadro's number in the window below. All right, let's go back to our question. Turn stuff around. Okay. Give me small again. Okay, so back to the question. So I have the number here, so let's just make sure our sig figs are all good. So the number we started with has 3 sig figs. So our answer should be to 3 sig figs. Ooh, and I forgot my unit. So the answer here will be 3.10 times 10 to the 22 molecules of Prozac. Okay, so the next question, how many fluorine atoms are in this 15.9 gram sample? So we're going to have to use another conversion factor that can relate molecules, like, because in the previous question we got how many molecules of Prozac there are. All right, so we can use the chemical formula to tell us the ratio of fluorine atoms per one molecule. I can see one molecule of Prozac equals, is it three? Three fluorine atoms. So this is another conversion factor that I can use. So I can actually just take the number from the previous question and then just apply this new equality, this new conversion factor. So I'm going to take 3.0955 times 10 to the 22 molecules times one molecule of Prozac is 3 fluorine atoms. All right, so if you stick that into your calculator using that E button to replace the times 10 to the part, you get, I think the answer is 9.285 times 10 to the 23 fluorine atoms. Again, we need to have 3 significant figures because our 3 sig figs, because our beginning number had 3 sig figs, 3 fluorine atoms, these are exact numbers. So those ratios, the subscripts on in the chemical formula, all of those numbers are exact, have infinite sig figs because they're exact numbers. So we don't have to be limited by the one digit, one sig fig on this 3. This 3 actually has infinite sig figs. So if I rewrote my actual answer, it would be 9.29 times 10 to the 23 fluorine atoms in this Prozac sample. So we've only talked about molecules, covalent molecules so far, but we can still apply the same things to ionic compounds too, everything that we just said. You can still calculate molar masses and formula weights of ionic compounds. So here's an example. We have calcium chloride. The ratios still mean the same thing, and you can still take those values off of the periodic table, where the formula weight for calcium chloride will be an AMU. This is calculating the weight of one formula unit calcium chloride. So this is our formula weight, and that's an AMU. Versus if we had a mole's worth of this compound, calcium chloride, this is our molar mass. So it's still the same thing with those same units that we talked about previously. So if you went ahead and calculated the molar mass of calcium chloride, you would get 101 grams per mole for that specific ionic compound. Avogadro's number is also applied the same way. If we have a mole's worth of formula units, or formula units meaning calcium chloride, we had a mole's worth of calcium chloride, that means that we have 6.022 times 10 to the 23 formula units, or formula units of calcium chloride. And the ratios still mean the same thing. If we have 1 mole worth of calcium chloride, that means there's 1 mole worth of calcium 2 plus ions present. If we had 1 mole of calcium chloride, we would have 2 moles of chloride ions present because of that 2 subscript. So basically, I can ask you very similar questions involving grams, moles versus molecules or formula units for ionic compounds, just like we just went over with the caffeine and Prozac molecules in the previous examples. So I'll just kind of recap the different mole conversions, how to get from grams to moles to molecules, and how those all relate. So, remember, on an exam, maybe you want to write this at the top. To go from grams of a substance, you need to go through moles, and then that can go to atoms or molecules. or formula units of a certain chemical formula. And you use different quantities to get between these three um, different quantities, grams, moles versus atoms. If you want to go between number of particles or atoms and moles, you'll use Avogadro's number. So use Avogadro's number. Whoops. If you want to go from grams of a substance to moles of a substance, you need to use the molar mass that's off of the periodic table. So use molar mass. And then finally, we just introduced ratios. So this is kind of this is our new type of conversion. So if we want to go from moles of a certain compound to moles of a specific atom in that compound, we have to kind of go from this middle track here. Once we have moles of the compound, we can go to moles of a specific atom using the chemical subscripts, those ratios. So moles of atom in compound. And you'll use a different color, use the subscripts. If you want to go from individual molecules to the number of individual atoms in a molecule, you can go from this part of our little roadmap here. So if you are already in molecules, you can get to atoms also using atoms of element in compound. You would also use the subscripts. That's what we just kind of did with our fluorine example of Prozac. So you'd also use subscripts. And actually, these two places where we're talking about moles of an atom in a compound versus the individual atoms of the element in the compound, this is related by also Avogadro's number. So there's a multitude of ways to get to singular atoms in a compound, but you must be in the unit of moles or singular molecules, individual molecules. So let's do some practice problems, practicing navigating this roadmap that we kind of just made. All right, so we have this problem. So lithium carbonate is used to treat manic depression. How many lithium carbonate formula units, so lithium carbonate is a ionic compound, are present in a 550 milligram tablet, 3 sig figs? And how many lithium atoms are present in one tablet? So this question is asking two different things. How many formula units? How many lithium atoms? So let's just focus on the first one first. So let's just kind of take a look at our roadmap. The value that's given to us is grams or like milligrams of the tablet. So we're starting here. We're starting here on our roadmap. We're in grams of lithium carbonate. It's asking how many lithium carbonate formula units are there. So we have to go from grams to moles to formula units. So we have to go this way. So you see we have to use molar mass, Avogadro's number, to get to formula units. The second part of the question, how many lithium atoms are present in this tablet? So we need to get over here, atoms of the element in the compound. So we'll kind of take the same path. We need to go from grams to moles to formula units, and then take one more step to get to atoms of the element, and you see that, or atoms of the compound, and you see that we have to use subscripts here. So I've kind of written my strategy here. Well, first we need to determine what is the molar mass of lithium carbonate, because in order to get from grams to moles, we need to use the molar mass. We also need to convert milligrams to grams. That's pretty straightforward. And we need to convert moles to formula units. So again, I'm just kind of laying out our roadmap here. And then finally, determine the number of molecules, the molecule to, or this really should say formula unit, to lithium atom ratio. So we have to figure out that ratio, and that's using the subscripts. All right, so that is our strategy. Did I give myself space? Yeah, I gave myself space down here. All right. So keep that roadmap in mind. Right now we are in grams in a mass. So the first step to my strategy was let's figure out the molar mass of lithium carbonate. So there are two lithiums, there's a carbon, and there are three oxygens. So let's go ahead and get that molar mass. Do I have that here? Yeah, so two lithiums is 6.94 grams per mole, or AMU. One carbon is 12.01, and oxygen is 16.00. All right, I'll just show all my work here. And you see that all the lithiums added up is 13.88 grams per mole. We have 12.01, and we have 48. And so if we add that up, we get the complete molar mass of lithium carbonate, and that is 73.89 grams per mole. All right, so there's our molar mass of lithium carbonate. So using that quantity, we can get out of the mass, the gram mass that we have, that we're starting with. Because we're starting with 750 milligrams of the tablet, which is lithium carbonate. All right, I don't want to be in milligrams, I want to be in grams. So there's 1,000 milligrams in 1 gram. So now you see, instead of being in milligrams, now we're in grams. So now I can use that molar mass that I just got here. All right, so if I rewrote that molar mass as a conversion factor, remember it's 73.89 grams of lithium carbonate is equal to 1 mole of lithium carbonate. So since gram is in the numerator, I want to put 73.89 grams on the bottom, 1 mole of lithium carbonate up top. All right, and it's asking for formula units. So if you look at the units now, grams cancels. So now I'm in moles of lithium carbonate. So if we look back at our roadmap, we're here. We went from grams to moles by using the molar mass. Now we need to get from moles to formula units. We need to use Avogadro's number. Go back down here. All right, so 1 mole of lithium carbonate's on up top, so I want to put 1 mole on the bottom. And so Avogadro's number is 6.022 times 10 to the 23 formula units of lithium carbonate. I need to add a page. Okay. So if you stick that into your calculator, so I showed how to use the two calculators now, so I think we can do this now. Do I have this here? All right, so I quick put that in my calculator, and I got 6.11 times 10 to the 21 lithium carbonate formula units. And so this has 3 sig figs because the number we started with also has 3 sig figs. So 6.11 times 10 to the 21. All right, and so now the second question says how many lithium atoms are there in the tablet. So again, look at our roadmap. We're right here. We're in formula units. So in order to get to atoms of a certain element in the compound, so in this case lithium, we need to use the subscript that's there. So the subscript that relates the formula unit lithium carbonate, there are 2 lithiums for every lithium carbonate formula unit, or you can think molecule, that there is. So if I start with this number, 6.11 times 10 to the 21 formula units of lithium carbonate, right? So for every 1 lithium carbonate, there are 2 lithium ions there. So I'm going to put 1 formula unit of lithium carbonate on the bottom and 2 lithium ions up top, or atoms, whatever. All right, and so just multiply that number by 2, and you get the answer is 1.22 times 10 to the 22 lithium atoms. So we just essentially navigated the entirety of that of that quantity roadmap up here. We went from grams to moles to formula units to atoms. So this roadmap is very, very important, and I highly suggest you making your own so you can clearly understand how to navigate that and which quantities you need to use. When do you need to use molar mass? When do you need to use Avogadro's number? To get between these different amounts. Like if I ask, I want grams or moles of something, you can clearly see which quantities that you need to use. So let's do some more practice problems. Everybody loves practice problems. All right, so here's another one. The artificial sweetener aspartame has this chemical formula and is used to sweeten soft drinks and other things. So how many moles of aspartame are present in this many grams of sample? So it's giving us grams and we want to get to moles. So if you look at that roadmap, in order to get to grams of a substance, to moles of a substance, we need molar mass. And because this is a compound, we need to take that extra step and calculate the molar mass of the substance or the compound. And thankfully, they give us the chemical formula for that. So it should be pretty straightforward. So we need molar mass of the compound. So let's get that. So they give us the chemical formula. So there's 14 carbons. All right. So the molar mass of one carbon is 12.01 grams per mole. 18 hydrogens, 0.008 grams per mole. There are 2 nitrogens, so that's times 14, and 5 oxygens, and that is times 16. All right, so if you add that all up, you get 294.304 grams per mole. So that is the molar mass of our compound aspartame. C14H18 N2O5. All right, so we're going to use that to go from grams of our substance to moles of the substance. So I'm going to start with the number given, which is 225 grams of aspartame. And I'm going to use that molar mass that I got. So grams needs to be on bottom, so 294.304 grams needs to be on bottom for every 1 mole of aspartame. And so you see that the units now of grams cancel, and we're just left with moles, and that's exactly what we want. So that answer now is 0.7645 moles. Let's check our sig figs. 3 sig figs, so I want to round our answer to 0.765 moles of aspartame. All right, so in that example, we didn't have to go too far in our little roadmap, but just make sure that you know how to navigate it. Don't do more work than you have to. So to round out this section, let's do another practice problem looking at an ionic compound of ammonium phosphate. So I have that here. This is an ionic compound. We're talking about formula units, and I actually give you the formula weight for it for this compound so you don't have to calculate it yourself. The formula weight is 149.12 AMU. That's the mass of one formula unit. So just one molecule of this. So you can also write the molar mass of this compound as 149.12 grams per mole. So depending on what we want to do, I usually like to work in molar mass. So, all right. So this question, I might need another page here too. So this is a multi-parter. So the first question here is asking how many moles of this ionic compound do we have in a 359.2 gram sample? So we want to go from moles. Oh, no, sorry. We want to go from grams because it gives us grams. We want to go from grams to moles. So if you look at the roadmap, we need molar mass, which they give us. Fantastic. So let's do that. So we're starting with 359.2 grams of our compound. All right, and we want to get to moles. So We'll use the molar mass that's given right here. So 149.12, is that what it is? Yeah. Grams of that compound is equal to 1 mole of that compound. All right. So you stick that into your calculator and you get that there are 2.4087 moles of NH4 free phosphate. All right, let's just take a look at sig figs. Okay, there's 4 sig figs in our starting number, so we need to round this to 4 sig figs. So our actual answer is 2.409 moles of NH4 ammonium, 3 of them phosphate. Okay. All right, so that's the first one, where we just had to go from grams to moles, so we use molar mass. So now it's asking how many formula units of the compound are in 359.2 grams of the stuff. So we want to go from grams to formula units. All right, so we want to go from grams to formula units. So we need to go through moles. All right, so we kind of did one of the steps already where we went from grams to moles using molar mass. Now we need to go from moles to formula units of this compound. So we can actually use the answer that we got from the previous question here. So we need to go from we can go from moles of the substance to formula units, or molecules of the substance. So I'm going to start with this value here. So 2.4087 moles of the stuff times, in order to get from moles to formula units or molecules, we go all the way back to our roadmap here. In order to go from moles to formula units, we need to use Avogadro's number. Let's go back. So we're using Avogadro's number here, 1 mole, 6.022 times 10 to the 23 formula units of the substance. So if you put that into your calculator, you get 1.4505 times 10 to the 24. Again, note sig figs. It has 4 sig figs. So our answer needs to be to 4 sig figs. So this is 1.451 times 10 to the 24 formula units of NH4 ammonium, 3 of them phosphate. Okay, there's our answer to that one. Okay, what's the next one? So the next one says, how many ammonium ions are there in the same massive sample? So we need to go from formula units to a specific ion, but we can set up a ratio because of the formula of the compound itself. For every one, I'll say formula unit of an NH4, 3 of them phosphate, there are 3 NH4 plus ions. That's what the parentheses, there's 3 of them. There's 3 ammoniums in every full unit of this chemical compound. So we can use this ratio to get to the answer that we need. How many ions are present in this sample? So I can take this previous number again, and essentially I just use the ratio from the chemical formula. So if you look back at our roadmap, we're already in formula units. We just need to use subscripts. So the down arrow that I have, use the subscripts to get to, in this case, a specific polyatomic ion in the chemical formula. So in this case, it's not a specific atom, but that's okay because we can still use the ratio that's there. So I'm going to start with 1.4505 times 10 to the 24 formula units of NH4, 3PO4. Let me move this. Okay. So I will use that ratio I just got. For every 1 formula unit of the compound, there are 3 NH4 ions. So I'm essentially just multiplying that number by 3. It's like saying if I had, 1.45 times 10 to the 24 cars, how many wheels are there? Well, for every one car, there's four wheels. So that's like saying you would put one car on the bottom, four wheels up top. Now you have, as the units cancel, now you have a unit of wheels. So, all right, so if you stick that into your calculator, you get 4.3517 times 10 to the 24 NH4 ions. But again, sig figs, we need to round to the four sig figs, so 4.352 times 10 to the 24 NH4 plus ions. There's our answer. Whew, okay, what's next? So now it's asking how many nitrogen atoms are in the same amount of sample. All right, so let's think about the formula units. How many nitrogens are there in one formula unit? So one formula unit of our compound, let's look at how many nitrogens there are. So you see that, I've only written, there's a one subscript implied to this nitrogen, but remember this whole thing is multiplied by 3. So there are actually 3 nitrogen atoms present in that chemical formula. All right, so every 1 unit of ammonium phosphate, there are 3 nitrogen atoms. So if we do the work there, it's actually the same work we did up here, where you just take the number of formula units you have. Let's paste that, copy, paste. All right, so it's actually the same work. So times 1 formula unit is equal to 3 nitrogen atoms, and it's actually going to be the same number. So 4.352 times 10 to the 24 nitrogen atoms, because the ratio is the same. But I saw that because of inspecting the chemical formula. All right, last one. So how many hydrogen atoms are in this same sample? So now we need to go to hydrogen atoms. Again, let's just inspect the chemical formula. So if we look at the formula here, all right, hydrogens here, there's 4 of them. But remember, this whole thing, there's 3 of them. There's 3 ammoniums, where each ammonium has 4 hydrogens in it. So there's actually a total of 12 hydrogens there. So we can say 1 formula unit of our ammonium phosphate is equal to 12 hydrogen atoms. So we're actually going to pick up right where we left off using that same number of formula units as we did before, but now we'll just use the ratio for hydrogen instead, which is 12. There are 12 hydrogens here because of the parentheses, subscripts, and 4 hydrogens. So 4 times 3 is 12. So for every 1 formula unit, there is 12 hydrogen atoms. And then that number is 1.7406 times 10 to the 25. Again, 4 sig figs. So it's 1.741 times 10 to the 25 hydrogen atoms. All right. So there is that question. That one was a little bit more involved. It required you to inspect the chemical formula of this specific ionic compound to use those subscripts to navigate the different amounts of atoms in a particular sample. But they gave us the amount of sample in grams, so you have to get to number of formula units by going through from grams to moles to formula units. You need to go from grams to moles using molar mass, while you go from moles to formula units using Avogadro's number. All right, so I will provide a handout where you can practice navigating moles of substance, grams of substance, molecules or formula units of different substances, and using those ratios. This is a very important skill to learn, and I can promise you there will be a question like this on midterm 2 where I give you the mass of something and you need to figure out how many atoms of something is present.